Hello, everyone. My name's Anika Schmiedeke. I'm a scientist here at Green Bank Observatory now for 3.5 years by now. I work mainly with the high frequency receivers, so mainly the Argus friend. This is the reason why I'm giving you the high frequency corrections talk. Other than that, I use some of the medium frequency receivers and very rarely venture into the low frequency regime. So today focuses on high frequency corrections in this talk. Even if you're right now being trained on doing more focused on low frequency observing, it's still interesting to learn about what we need to do when we want to observe at high frequency. And if you ever get into the position where you need to start observing or want to have an idea for a project at high frequencies, and vaguely remember there was something that you need to take off, just connect to us. As Tony said, we are here to help you, to reach out to your project friend, and we will be happy to help you, even though you're already fully trained on everything with the GBT. It's understandable if you haven't used these things and have done these corrections that we run you through them. We're happy to do that. Now, this talk, I will start off with revisiting some of the GBT optics. I'm pretty sure you've heard this, but let's revisit it. So our dish is 110 meters by 100 meter cutout of a much larger parent parabola, so a 208 meter dish. So here you have the GBT, and it's part of just a larger parabola. The feed arm, that's the arm that supports the receiver, is off axis, which allows for a very clean signal pass. So you have the signal come in. If it happens, give me a second. Here it comes in, signal coming in, hitting the receiver. And the little sketch here, it hits the prime focus receiver with the boom arm being extended just in front of the secondary. If the boom arm were not extended, then the rays would hit the subreflector up here. I'm not sure, can you see my mouse?
Yep, we can see it.
Excellent, because I'm pointing with the mouse and I just, okay, the rays get reflected on the subreflector into down here, which is the receiver cabin and where all our Gregorian receivers are sitting. And those would be the high frequency receivers that you use for high frequency observing. Now, in terms of high frequency, what we have is like the W band, Argus, and Mustang 2 are the main high frequency receivers. Q band to some extent too, if you want to. What makes the GBT special is the active surface that we have. Here's a very close-up view of our surface, of the dish surface, or the edge of the dish surface. And you very prominently see these 4 actuators. We have way more, but those basically what the actuators look like. They are 2,209 actuators for 2,004 panels. So our dish is not just one big giant metal sheet, but it's rather a panelized, a large surface made out of individual panels. And then at the edges of these panels, we have these 1D actuators sitting. They move in 1D, they move up and down. And with that, you can shape the dish to get the perfect parabola that you would need, or that you would want basically for high frequency observing. Now, when we observe that, we are mainly concerned about the formations and deviations from the perfect parabola, and that's the main focus of high frequency corrections that we need to do. So let's look into what can cause deviations, you might ask. So for one part, deviations can be caused very simple by gravity. We have a 100-meter dish. So if you move that dish and change the elevation of it and the angle where it looks, then of course gravity pulls different in different parts of the dish. For that, we have something that we call the gravity-Schmiedeke model. We have a model that corrects with elevation automatically the terms and the shape of the dish. So you will not even notice that this is running, but this is run in the background and it will do corrections for you. And then another effect on the dish is differential heating. That's during the sun, the structure, during the sun, oh my God, during the day, the sun's up, of course, and that heating heats up the dish. And then it also heats up the ground. And at night, we have the heat being evaporated from the ground, heating the background structure of the dish. So we have just different levels of temperature around the telescope. which can cause deformations, and you want to correct for that or account for that. Now, years ago, there has been a lot of work being done on the active surface, and what I'm going, and we made significant improvements to the active surface. In the top, I will show you basically what the surface looked like. And in the bottom, you will start seeing the 11.7 gigahertz beam pattern. And we'll look at that for different times, so January, February, March, and September in 2029. So in January, in the surface map, what you can see is there's a lot of color deviation, so to say. So everything that is bright white or dark red shows a large offset from the large parabola, from the perfect parabola, which means that we have either broken actuators or patches that are not working well and just deforming the dish. And you see a very, very widespread beam pattern. And now, hopefully, when I show the next ones, you will see the improvements. So we fixed broken actuators. We adjusted the 0 points of the actuators. You start seeing this surface map become cleaner and cleaner, so becoming more like the just orange colored. And then also what you will notice is with the improvements towards the end that the beam becomes way more focused and way more concentrated. So the PSF becomes better. And that's exactly what we were aiming at. That was a giant improvement back then. Then another way to look at the surface improvements by adding the gravity model and the active surfaces. I will show you here on the left side plot the surface error as a function of elevation. So going from 90 degrees to from 0 degrees to 90 degrees. And then I will show you the aperture efficiency. So how efficient are you actually at different wavelengths? Now, these are not to the same scale. So notice that the scale on the y-axis is just slightly different. This is to highlight that we are getting better, but obviously at 10 gigahertz, we have a much higher aperture efficiency than at 110 gigahertz. So in 2023, this was not very efficient. I mean, it was overall okay, but it's absolutely not efficient at high frequencies. You wouldn't even consider doing high frequency observations here. And overall, what you can see from that peak is that the efficiency is pretty good at around like 40 to 60 degrees elevation, but at the very high or at the very low elevations, the efficiency would just drop significantly, the aperture efficiency. And the same with the surface error. This is now inverted. The surface errors go up at lower elevations and at higher elevations, respectively. Then in 2009A, and there will be a 2009B, we fixed the actuators and set the 0 levels. So you start seeing the improvement of the surface at the lower and higher elevations. So that's a quite good improvement. But overall, the efficiencies do not go up yet. Then there were more fixes being done, and that is towards the end of 2009. We have shown you before on the previous slide the very small beam and the collimated beam and the very nice clean surface. And that made a giant improvement in the surface accuracy or in the surface error. And it improved significantly the efficiencies. And if you look now at the 110 gigahertz at the very high frequency that we observe here, at least in the 40 to 60 gigahertz degree elevation regime, you can now start to observe it efficiently. And then in 2014, the gravity Zernike model was overhauled and the gravity model was put in. And now you actually see the full improvement of all the things that go on in the background that the scientists here do to help improve the efficiencies of the telescope. So the dark green line now shows you that we are quite efficient overall. These gravity and thermal deformations, they cause in general random large-scale errors in the dish. And here I show you the receiver response on the dish. This is how the receiver basically would illuminate the dish. It is tapered to the outskirts of the dish, so it's like dropping off. And we get the best response in the middle of the dish. On the right, you see the surface errors. When you do high frequency observing, these are the type of maps you would look at the beginning of your observing sessions very frequently. Overall, mean, just to interpret this circular structure, as you probably have guessed already, that's the dish. That's the size of the dish. Lighter colors in here refer to deviations above the perfect parabola, and darker colors are deviations below the perfect parabola. So what you generally would want to have is something that is more in the middle and in that sense around zero, like the orangey level kind of structure. Also, what one want to see with here is like gentle features across the dish. Here we do see gentle features in the center, and then sharper features marked by these contour lines. You see there's way more contour lines staggered towards the edges. That's quite common. In order to model these errors, we use Zernike polynomials, the same that are being used in the optics. You hopefully have heard of them at some point. So they're a set of orthogonal polynomials that are used to reconstruct geometric features across a circular aperture. They have been derived by Fritz Zernike, hence the name Zernike polynomials, in 1934. And these polynomials are essential in determining the beam optics. On the 0th order, they are just an offset. On the 1st order, it's basically a gradient across. And then in higher orders, you get more and more complex geometric shapes, and these are the ones that we actually then apply. So it's a superposition of those polynomials, excuse me. When you observe, you of course do not have to sit down with pen and paper and determine them for each observation. This all is included in the processing software that you observe. It runs in the background, but this is just to give you an understanding of what is done during the processing before you see the map. Let me go to the next slide. Here we go. So what we do to get the surface improvements, we use a technique that's called out-of-focus holography, or we just call it OOF. Or if you run it here at the GBT, actually it's auto-OOF that you hear very often, because a lot of the stuff is automated, and we use the auto function for OOF, or OOFing, as it turned into a little verb here, OOF here. This is the, in the top you will see the measured data, and the bottom is the simulated data. That's the simulated maps that are being calculated. And what the out-of-focus holography is doing, or what you need to obtain in the course of the running the out-of process, is a map in focus on your calibrator, a map that is defocused in the positive direction. In this case, at 43 gigahertz, it's an offset of 35 millimeter in focus. And then you do a third map that is offsetted in the focus by minus 35 millimeter. Now the amount it gets defocused depends on the receiver and scales with frequency. So for Argus, it's something like 12 millimeter, for example. So the higher you go in frequency, the less you need to defocus to measure the surface accuracy. But the key point to take away here is when you run an auto-OOF, it always will automatically do 3 maps in a row, and you just have to wait till that is done and the data is obtained. Now, what you need for auto-OOFing, you need a bright calibrator. You basically want the brightest calibrator on the sky. If you're lucky and you have like 2 or 3 very bright ones up, then you can of course choose the one that's bright closer to your source. But what you want ultimately is the brightest one that you can find on the sky. And that is because, as I said in the slide before, you have to do 3 maps, or 3 maps are being done to get the surface corrections, and 2 of them are being significantly out of focus. So you need your source to be strong enough to still be detected when you look at it and it becomes very, very blurry, essentially. But you still need to detect it. So how do you find a bright calibrator? For us, I typically just go to the ALMA calibrator source catalog. This overlaps with us in band 3. So band 3 is the 91 to 103 gigahertz. There's a slide missing here. I'm sorry. I wanted to show you the query form. So in the query form, if you go to one of the links that are listed up here, they all lead to the same page. It's just ALMA. It's the 3 parts, the European, the American, and the Asian part. For the calibrator catalog, but it's the exact same database and the exact same catalog. what I just put in the query was give me all calibrators above, I believe, 5 or 10 Jansky that are in band 3. And this is the list that came out. You can adjust the numbers there, or if you already know your calibrator and you want to check if it's wide enough, just put your calibrator name in there. You will get a result table. And then if you click on the result plots, you get them all plotted with their flux density. So in that case here, I already clicked on that little dot up here, which is 0319 plus 4130. It's my personal go-to calibrator when I observe, because it's near my source that I like. But this is very handy to look at it, see how strong it is at the frequency. It's all interactive. You can zoom in here, and then you can look into the last couple of months if you want to. You can hover over individual data points and you get the exact flux density at that with the uncertainties. These are for 2 different frequencies, so it's 91.5 and I think 103 or something, a higher frequency, which is the lower line up here. But that's quite handy to look at and figure out which is a strong source at the moment, because as you see, they do vary in their strengths. Now, to run an auto-OOF with our receivers, the receivers you can use to run it to are the Ka band, the Q band, W band, Argus, and Mustang 2. No other receiver can run an auto-OOF, so you need to have one of those. Yeah. I will run you through how an auto-OOF observation looks like and what's being done. For the example of Argus, other receivers are fairly similar. In the case of Argus, the first 2 scans will be what we call a vane cal. So you're just calibrating your temperature scale. Looks like that. There's not much in there, but the important part, what you get out here is the system temperature that's marked here in the bottom. For Argus, 107, that's quite normal. That's okay. If you were to run this with W band, it would be what's called a CalSec, I think, because it has a calibration wheel. And for Mustang, it would be a SkyDub observation that's being done at the beginning. For Ka and Q, there's nothing run at the beginning. They have noise diodes, so they calibrate through the noise diodes. And then for Argus, the 3rd scan is actually the first OOF map scan. This is what will happen when it takes it. The observing panel will switch automatically to this OOF panel. You will see a picture of the GBT, and you can look at that for the time it takes to obtain the OOF maps. It tells you in the bottom that it's currently running OOF map 1. What you can do is, once the map has been taken, is you can switch to the continuum panel. You would have to click that, but you can switch over there. And what you see in this continuum panel is basically a timeline. So it started taking the map over here, and then, as you know, it's a RA long map. So the telescope scans and over the source, and at some points the beams hits the source and just a fraction of it, and then more and more and more. So these plots are very good to look at to see if your calibrator is actually strong enough. You want detection of your source in this view and in this look, in this time scan look. Then I show you the one for the second map that got completed. This is now, remember, the first one that is positive defocused. So that one, of course, well, is lower in frequency. And then it's low in frequency. It's low in intensity, my apologies. And then the third one is the same, also lower in intensity. If you've done this now a while, then you will already see that if we go back to this one, for example, from the timeline plot, you can tell that there will be a pointing offset. So the pointing is not quite perfect. And that's because the maps are generated in a way, the map trajectories are that the source is expected to be at the center, which means it should pop up in the middle of the timeline, but it's coming up later in time. So there is a pointing offset already present. And then by comparing the defocused ones by eye, one can already tell that there should be, oh, sorry, I'm going in the wrong direction. That there should be also a slight focus offset, because in one of the focus scans, it's a little lower in intensity compared to the other one. So, you know, there will also be a focus. You don't have to worry about this. This is just stuff while one sits and looks at them over time, one recognizes that and notices that in the plots. So once the third map is taken, there will be this little button here. Right now it's filled already, but during the processing, it will slowly move up. Takes maybe a minute or so to complete. And once it's completed, it will show you the surface map that we've looked at before as well. So that's the typical surface maps that show up. It always defaults to the Z5 here, so you'll always see that. Takes a few minutes, we had that. Now let's do a few of the parameters. So this is the window you spent a little bit of time at clicking around and looking at some things to judge and figure out, is that a good solution? Should I apply it to the telescope or not? So if we look at that, then this is the panel up here marked in the green box that you want to play around with in that sense. So first of all, I would always have a look at the numbers here. What you see here in the brackets are the LPCs, the local pointing corrections that it derives. The first one is the one for azimuth, and the second one is the one, cross elevation, and the second one is the one for elevation. And these are in arc minutes. They are pretty much the same, so that's a good indicator. It's a good solution, most likely. And then you look at the focus Y correction, local focus corrections in the Y directions, and they are all pretty similar. That is good too. If you see higher jumps here, or jumps, that usually indicates there's something going on with at least one of the data sets in there. So then you can click through. That's the surface map for the Z1, Z4, and we had the Z5 just before. So I apologize. I'm clicking in the wrong direction here. So that's Z5, Z3, and Z4. All of them are pretty smooth. There's quite clear separation between the different contour lines. That's all a good sign. Another thing to look at is the raw data. What you see here now is the raw data on the top. The raw data after baseline removal. Now for an Argus observing scan, usually the baseline is not horrible. We are pretty flat for these type of scans usually. And then at the bottom you see the observed beams, so the beam map that was taken. And then it follows in the three. So this is the first map in the vertical, and then there comes the defocused, the positively defocused one, and the negatively defocused one. You can just look at the data and see the quality of them. And now it shows what I was saying. So in the timeline, the lines appear a little later, and we have a larger pointing offset in the elevation, 0.05. You also see in the map, it shows up further in the top. It's not quite centered right. So that was the pointing offset that I hinted at in the previous slides. And then for the focus as well, the minus 12 millimeter gives you higher intensities than the plus 12 millimeters. So overall, the focus shift should be towards the negatives, and that is what it is. So that's all good. And then in another is the fitted beam maps. You want to look at that too. In the top, you have the observed beams, and then you have the fitted beam maps for the different solutions for the Z3, Z4, and Z5 fits. And then in the vertical, you have the exact same as in the previous. So the focus, defocused in the positive direction, defocused in the negative direction. And what you want to look at here, I mean, these all look, when you look at them, that's exactly what you what you expect. They are pretty fairly round and smooth in the focused at 0 millimeter focus. And then they get elongated and smeared out basically when you defocus, and they are all pretty consistent. So all of these solutions are good solutions. Typically what we then say, if everything looks fine, you mark one of the solutions and then you click that button that may or may not be green. You just click that button and the corrections will be sent to the telescope. So that's the interactive part where you look through all the maps and you make your decision, and then you send the solution that you want applied to the telescope. Now, if there was something wrong and you're like, nope, I don't like any of that, this is all weird, you might have accidentally already clicked or so. You can always click the 0 and turn off thermal Wernicke solutions, and then rerun the OOF if needed. So there's options down here. And if you think you've messed something up, but you ultimately want to 0 and turn off everything there, then you can also let the operator know, and they will do that for you in the settings. Now, how to check if things have been set. This is the Clio status window that I like to look at for this. So up here in this panel, I know it's a bunch of numbers and I'm not sure how much you guys have seen through that, but this is something you will probably look more at when we observe tonight and tomorrow night. So over here, you find the local pointing corrections for the azimuth and the elevation. And that should reflect the numbers that you've seen in the panel just before. This is for a different project, so not at the same time. So they, of course, don't match right now, but this is where you should see your numbers pop up. Then this is the local focus corrections. If that button is turned green, then the YFC should be the number that you saw in the focus corrections in the previous plot. Another thing to look at and that you want to check for making sure everything has been applied to the telescope properly is you go to the devices tab down here and you scroll. There's a scroll bar down in the bottom and you basically go all the way to the right. And then there should be a panel that says active surface. And you see a bunch of information on the active surface, but the important part that you want to see that the Z thermal coefficients, so the Zernike thermal coefficients, are being used. So they have the green box mark in the front here. That means they are turned on and have been sent to the telescope. So your corrections have been sent to the telescope and are being used. You also want to make sure that all the others are off if they are not are on, so are green. When you run high frequency observing, they should all be green. If they're not, there's something else going wrong, and you likely have not gotten good thermal coefficients to begin with. But that's the operator will take care of making sure that everything here is set. If you run Argus observations, then, and you have already configured Argus and balanced for observations, then it's also worth looking over here, making sure that the Vegas numbers are just at the around -20. That's what you want to look at for. If you observe with any others receiver in spectral line mode, you also want to check. I mean, it's a good thing. I always make it a habit to check the Argus levels. That's a way to look at that. You may just not use all the banks depending on your configurations. You might not see all of them. So this will always adjust to these windows down here in the devices will always adjust to what you actually configured the telescope for. So some of that may be there or may not be there. But if you use the active surface, this definitely should be there. Now, a comparison of out-of-OOF raw data streams. I've shown you only one before, but here's a comparison of one that we would call a good one on the left-hand side. This was the same stream as I've shown before, where you have the raw data after baseline removal and the observed beam maps. And you clearly see your source, you see the spikes, this is all good, this can be used. You also see the baseline ripple here that becomes flatter after the baseline removal. That's a good thing too. So this was done with Ka band, it says that down here, okay. And then the other one, that source is too weak. You barely see your source in the regular focus map, and then it's basically gone in the other ones. So it's too weak, you cannot derive your solutions from that. That's an indicator you need to repeat with a stronger source. Another example of a bad out-of solution. In this case, the observations were done in the keyhole, so meaning at an elevation higher than 85 degrees. You get an OOF RMS of 438, which a large, if you look over here, the implied elevation pointing offset is ginormous. It's 0.8 arcminutes. That's a lot. So yeah, you don't really want to use that. One caveat though, please don't just go and look at the RMS down here, the surface RMS, and say like generally if it is above 400, you cannot use it. There is a caveat to this. These numbers here, don't use it above 400 applies to when the LPCs, LFCs, and thermal corrections were zeroed out prior to running the out-of-OOF observations. If for whatever reason you have previous solutions in there, then that surface RMS is calculated with respect to those previous observations. So as a little caveat, one cannot just blankly use that number. One has to look through the maps and the fitted beam maps. Here's more on that previous observing. So when you looked also at the fitted beam maps for that example that I just showed, the observed beam maps, so the ones up here in the very first line, they should not be streaks or very elongated This can happen in windy conditions and so on. Then don't use the solutions. You have to try again, or yeah, mostly try again. So here's another example to run through. In that case, for some reason, the Schmiedeke 3 solutions were not good. You see they're very streaky. They absolutely do not fit the observed beam maps. Their suggested or calculated focus correction is very, very high. This is suspicious. I would not use that. You should, maybe if you're good with a Z4, Z5, you could apply those. If you have a bad oof, what do? Well, first you zero, if you have applied it and you're like, oh no, wait, actually it's bad, I should not have clicked. In that case, it's actually a green button. I should not have clicked that. Either zero them out or let the operator know, ask them to turn everything to zero again, and then rerun your oof. An option that you have, it's optional, but you don't have to, you can run an auto peak on your calibrator just to check the strength of it. Yeah, that's an option to do. And then you re-oof on that stronger calibrator. If you're using Argus, then what you can do if Ka or Q-band are up, then I would actually recommend using Ka or Q-band to observe, to run the auto oof with instead of Argus. You have a lot more sources available that you can run an oof on than if you were to use Argus. There's only very few really strong calibrators that you can efficiently do this with. And for Mustang, you use Mustang. They have very optimized routines. I would use Mustang. Well, you have to use Mustang. So now in the observing strategies, just to give you some pointers here, auto oof can be done with Ka, Q, W, Argus, and Mustang. It takes about 20 to 25 minutes. I usually, in my scheduling, when I make my observing block for the night, I usually account for 30 minutes. If I'm a bit faster, fine, but there's always some setup, and sometimes it takes a certain amount of time to click through the plots and so on. So with 30 minutes, I'm on the safe side for my observing planning typically. But yeah, the actual run time is 20 to 25 minutes. You can run it at night, or you should run it at night. You ideally want to run it after 9 or 10 local time. That's because if it was a very sunny time and the sun went down after sunset, it takes, of course, a while for the telescope to readjust with the temperatures to everything become similar temperature. If you had a big temperature gradient, the earlier you do your oof, the more likely you will have to re-oof because the temperature is still adjusting. And then depends on how much the temperature changes, the solutions are good for 2 to 6 hours, give or take. During the day, the surface changes on time scale shorter than an hour. It's not worth doing an oof. It's not worth observing. So for Argus, for example, we usually don't observe during the day. And overall, you want to use the strongest calibrator available. Then the other correction that you need to do, of course, is pointing and focus. That takes about 5 to 10 minutes to do. For high frequency, so for Argus, we should do this every 30 to 50 minutes. And you pick a nearby calibrator, something that's close to your source. For Argus, you can also switch to a lower frequency receiver, for example, X-band or KFPA. You have more sources available. There's other things that you then have to correct for. So if you have an Argus project, just ask us. We will help you with that. Now, with all these corrections and by setting the surface, what you can get down to is an RMS of 230 micrometer at night. And that makes the GBT the largest single dish telescope operating efficiently at 3 millimeter, which is very, very great. Another thing that I want to point out to you, probably have seen that by now, we have a user documentation hub. You will find a lot of information on there on the telescope. So that's just the starting page. But then specifically on the auto oof strategy, if you need to look at that, there's a guide that will be updated in the future even further with more information on auto oofing as a kind of reminder that one can look through. And with that, I am done for today. And I take questions.
Thank you very much, Anika.
I don't see anyone anymore. Everything's gone. Oh, over there. Now I see. Too many screens. I
And like Anika mentioned, for oofing, the high frequency groups will be having an oof example between the two observations tonight and tomorrow at between 12 and 12:30. If you're in a different group and would like to join and watch, you're welcome to do that as well.
This oofing, is this also important for mid or lower frequency, or is it just important for the high frequency?
So the range, I might not have mentioned that, sorry, that we recommend doing that after above 40 gigahertz. And then you mainly want that when you're really interested in like pointed source, anything extended larger than your beam, you do not necessarily actually need to oof. If you don't care about the extended part, you're just fine not oofing at all as well. But if you really want like for the beam structure, that size on that scale, then you should oof. Does that make sense?
Right. Nice. So below 40 gigahertz, you might use the time for observing. Thank you.
Yeah, yeah, yeah. And also we have some projects in like chemistry projects, pointed observations at Q band, and it's a very extended source. There's no need, no point to oof. You're not gaining much by that. You rather spend the time integrating and go deep. But yeah, 40 gigahertz is the where one should start thinking about oofing.
Nice. Thank you.
Any other questions for Anika? If not,
The video of the entire time? Oh my God, sorry.
yeah, that's all right. If not, thank you very much. And Dave, if you are hanging around, since you won't have a chance to introduce yourself to the whole group, if you wouldn't mind just introducing yourself and a little bit of your scientific interests and your role here at the observatory.
Hi, my name's David Frere. Yeah, I'm a scientist here. I'm actually the science division lead, so right now never mind. We're in yearly reviews of our staff documentation, so I'm doing that in the background. Um, I do gas and galaxies, both high redshift and low redshift galaxies. Focus primarily on infrared bright galaxies historically through my career. And in terms of what I do here, some of it I do is a lot of I help with a lot of those models in the background that Anika was referring to, and making and measurements and trying to maintain the performance of the telescope at the higher frequencies to enable us to do science up there at low wave, I mean short wavelengths.
And Dave and Anika are both leading the high frequency group, so they'll be there for the OOF session tonight, as well as the Mustang group. But like I said, if anyone else wants to call in and be a fly on the wall, please feel free to do so. We now have about 75 minutes, hour and 15, before we come back for the final observation prep session of the day. So I'm going to throw up a screensaver here, and we'll see you back in about 75 minutes for you to meet with your groups.
So, sorry, I have a question.
Mhm.
Is it possible? I don't know if I can make it, but is it possible to participate also? I'm in the mid-frequency group. Is it possible to participate also in the high frequency group, or there is any
Observing.
problems to do that?
I can give you a disclaimer. We are going to use KFPA. So if your group already is going to use KFPA, we
Okay,
don't
okay,
see ones up at the moment. We will give a ton of like information on what it would be with the high frequency receiver or where there's like differences, but the observing itself
okay,
will be done with KFPA.
okay,
And the
great. Thank you.
oofing part, if you can make it for that, that might be interesting. If you're high frequency interested, the oofing part, that will be Mustang tonight.
Okay. Maybe I'll try to be there for the woofing tutorial. Thank
Talk
you.
a little bit around the high frequency receivers are currently still in the lab being worked on. And
Okay.
All right. Thank you very much. We'll see you back here in about an hour 15.